members
Okay.
from various colleges, but then all no VLSI. They are from VLSI basically. Okay.
Okay.
So
Okay.
basic VLSI they are aware of.
Fine.
CMOS design, etc. Yeah. So we will have around 30 participants, you can say.
Okay. So I will prefer like to have an interactive session.
Okay, good.
Anyone
No
can
issues.
interrupt any time and ask.
Yeah, it's okay. No problem.
So I'm thinking to divide the talk into two. One will be the lecture part and other will be the simulation.
Okay. So
So
first you will talk about theory
about the theory, yes, yes.
up to
Then I will
around
show
one
how
hour.
we can
1
do
hour.
analysis.
Yes.
Yeah,
Around 1
we'll
hour.
take around 10. Yeah, we'll take a 10 minutes break and have a second session.
Okay. Your choice. Manisha madam. No, Manisha madam. Manisha madam, hello. स्नेहा मॅडम तुम्हाला आवाज येतोय ना माझा?
हा येस सर, आवाज येतोय मला.
Okay. I don't know there was no response from madam.
No, sir, you are calling for Manisha ma'am. That's why I didn't see it.
No. Yeah. She was there. But she was not
Okay, sir.
Shall we start with this?
Sir, are we starting?
I think we should start. No?
Okay.
Meraj sir, are you ready? Shall we start?
Yes, I'm ready.
Okay, so we'll start now. Manisha madam, can you unmute? I don't know. I think she's answering. Okay, I'll explain.
Yes, sir.
So, okay, good evening, everyone. So, good evening, Dr. Murthy. Nice to see your message. So, welcome back for this evening session. And I'm pleased to invite our next resource person, Mr. Meraj Ahmed. He's a research scholar at IIT Bombay. Mr. Meraj did his MTech in microelectronics from IIT Bombay. His doctoral research at IIT Bombay is on CMOS analog and mixed signal VLSI design. He was also the visiting research scholar at NanoLab, Tufts University, and he's also the embedded systems consultant. And since he's the research scholar at IIT Bombay, it is better that Meraj should speak rather than I will be consuming his time. His time is very, very valuable. So, Meraj, I'm going to hand over the access rights to you, and now the platform is yours. And looking forward for your session. Welcome to S.P.I.T and welcome to this session, Meraj.
Yeah, thank you, Professor Rathod. I will share my screen. So, okay, shall I start?
Yes, sir. Your screen is visible and audio is also very clear.
Okay, thank you. So, good evening, all of you. I am Meraj Ahmed from research scholar from IIT Bombay, and I am working in analog mixed signal IC design under the supervision of Professor Marine. Many of the slides are also the content in these slides are her feedbacks and input and what she trained me. So I should have acknowledged in the beginning. And I will talk mainly about dynamic offset cancellation techniques, which is a very common technique nowadays and used in very almost all analog IC design papers for precision applications. So we'll see like how, so I will divide this talk into two. One will have a theoretical understanding in time domain, frequency domain, how this technique works. And then we will also try to simulate a simple chopper amplifier in cadence. It is a bit different. We need to do a different type of simulation for this chopper amplifiers because it has its own way of operation. So we will have it a live demo also. So we'll start with first with the motivation. I have these 4 points. We'll talk about motivation, the chopping techniques, and some chopping applications, and we'll end up with a simulation demo. So now many analog circuits like op-amp, integrator, comparators, in ADCs, DAC, stage requires amplifier with offsets in the microvolt range. We need less than 1 microvolt of offset in these precision applications. So this is one of the core part which we will discuss today, like how we can uh, uh, we can make our amplifier, which has a, if you see a CMOS amplifier, the native offset is around millivolts. And we, from how one, from millivolts, we can achieve a microvolt precision. Also, there are some sensors which outputs the output is very small, and in that case, we need a circuit which has a microvolt precision. So, in this tutorial, we'll focus on chopping techniques with which offset can be reduced to microvolt level. There is also one technique by the name auto zeroing and correlated double sampling, which we'll not discuss. So I thought that let's focus one and let's go in detail understanding it. And if anyone have any doubt or question, can interrupt in between, because we have sufficient time, and I think we can take. It's better to take the question in between rather in the end. So what are these circuit non-idealities in CMOS? We have offset due to whenever we fabricate two transistor like differential pair, we'll never have a exactly matched transistor made on silicon. So it has an inherent offset, and that offset depends on temperature. Suppose in summer or also in morning or in evening, the offset will drift with time. So in that case, uh, uh, it's not like that we want to design a circuit which can work in summer, winter, morning, evening, and it should be very precise. So we need to take care about the offset drift, which is just small in bandwidth because it varies with temperature. And the two noise which are common in CMOS is 1 by F noise, which is also called a flicker noise or pink noise, because the noise, the spectrum depends on the frequency, and there is a thermal noise or white noise as it's flat in frequency, that's varying. So these are the four things which are which limits our precision in designing circuits. So we will use chopping techniques, how these things can be addressed. So especially these techniques are useful when our signal are in this range. As you can see in the screen, sometimes our signals are itself at DC, and the offset and drift will have an error and accuracy and precision issues. And also 1 by F noise is also a low frequency noise. So this type of signal which is shown on the screen, we use chopping technique to isolate these non-idealities with the signal, and this is what the whole lecture is all about today. So first we'll see, like if you take any recent, yeah, sorry, anyone have a question? No. Okay. Am I audible?
Yeah, you are audible. No question.
Okay, okay, fine, fine, fine. So, if you see any recent papers from any good transactions or journals, you will find some symbols for chopper symbols, and they don't go in detail because it's nowadays very common. So, you will either see this type of circular and a cross. This is a single-ended representation, and some papers you will see a differential representation like this. So, what is inside these two blocks? It is exactly a very simple structure which is made of four switches, and you can see that between this input and output, how these four switches are arranged. So two switches are controlled by clock and two are clock bars. So what it inherently means is when clock is high, the input is equal to the output, and when clock bar is high or clock is low, then you can see the positive is connected to negative and negative is connected to positive. So by this way, chopper is called as a polarity reversal switch. So that can multiply V in by either +1 or -1 based on the switch. And these switches are implemented with either PMOS transistor, NMOS transistor, or transmission gates based on what voltage level we are interested in. As we know that PMOS is good if we are near the supply rail, and NMOS is going near the ground. And sometimes if you want a full range, we use transmission gates as a switch in these four places. So how it works, let me go to the next slide. So earlier we saw the symbol, now let's see some waveforms, like how the input is converted and what is the input output waveform in time domain. We are focusing now on time domain. So if we see V in, and let's assume it's a DC signal of amplitude Vx, and we have a clock of some frequency that will be rail to rail from ground to VDD, and clock bar will be just inverse of it. So what will be the output? You can see that when VDD is high, V out is exactly the same as V in. And when VDD is low, so this switches turns on and we have negative of Vx. So by this way, what a chopper does is just of this switching arrangement and clock, it just multiplies by 1 and 0 based on the frequency. So this is one of the time domain representation for a chopper amplifier. But now what if we have two choppers in series? In this case, we have one V in and one V out. Now we are talking about V in, one chopper followed by another chopper. So what will be the V out? So we can see that similar, if we give V in as Vx and we have a clock, so this potential Va and Vb is exactly a square wave with amplitude Vx. And at V out, we can see that at clock we have exactly Vx, and at the ground we have minus of minus Vx, that is exactly Vx. So what it means, if we have two choppers in series, we can reproduce our signal back from DC to AC and again to AC. So this is the core idea of modulation and demodulation, and how it helps to reduce the offset. We'll see in the next slide. So let's assume in these two choppers we have one source VDC, this red one. So now how the waveforms will vary. Input, clock, and VA. It is similar to our previous slide. And this VB, you can see that this square wave has gone a bit up by just exact amount of VDC. And if VDC is large, this the square wave will go in positive direction more. So what will happen if we demodulate back the second chopper? What it does? So now on top we'll have Vx plus VDC, and when clock is low, we will have the negative of this term, that is Vx minus VDC. So what we come to know is that at the output we still have the information at the DC, and our offset is modulated at a square wave. You can see from Vx plus VDC and Vx minus VDC. So what it represents? It represents that the input, if modulated twice, the output remains at DC, and if a DC input is modulated only once, the output modulates to a clock frequency. So by this way, we are separating out. This is the core idea of separating out. Since our input was also at DC and our non-ideality is also at DC, so the idea is to modulate it to a higher frequency, then let the DC comes in, and then we demodulate again, so that we'll again get a DC, and this non-ideality, this offset voltage at the other square wave. So now what, to recover back, we need a simple low pass filter. So how it works is, this is a superposition view, like in time domain. We have input, we have a square modulated output. Then we can see that I have not shifted this graph up because it's a superposition. So we'll have this square wave and a DC, it will appear. If you have an ideal filter, what does an ideal filter do? It just removes this a higher frequency, and it will allow only DC term. So this is the frequency representation. Any signal in DC, if you calculate the Fourier transform, is an impulse. And for any square wave, if you take the Fourier transform, it is a impulse. It is a train of impulse with odd harmonics. So this is the third, fifth, and third, fundamental third and fifth. And now if DC adds to it, and when we demodulate, this shifts to the higher frequency and DCs come back. And in the end, at the output, if we add a low pass filter, ideal low pass filter, we can recover back our input exactly as it is. So it's like offset is completely removed, and by this way, exactly, this is the way which we are able to generate microvolt of precision. But nothing is ideal in this world. So what will happen if you have a practical low pass filter? So let me show you the spectrum. So if we have a practical low pass filter, we cannot eliminate the square wave and it will have some ripples. Due to this ripples, we'll have some error, and that's why we are telling that we can achieve at microvolt levels. Ideally, it should have eliminated offset completely. So now what this was a DC offset. Just this is all just to build up like how a chopper amplifier is made. Now what if I have an amplifier of magnitude 1 here in the center, something like this? The spectrum will be exactly the same because nothing has changed. Whatever input was VA plus VDC is exactly what VD is. Now what if we have a gain here, amplifier with a gain A? So what we have done is we have this is the exact model of an amplifier with an offset. You can see if we have a DC signal, it is amplified, it is modulated, and after the amplifier, the signal as well as the offset is amplified a bit. Then it is uh, demodulated, input comes back to DC, and we have some ripples. So this is an exact structure of a simple chopper amplifier, one at the beginning and one at the end. So this is the core part, and this is what we will simulate today. And we'll try to figure out like how to set up and how to see these noise and offset translations in cadence. So now what chopping techniques helps? It helps in mitigating, means reducing the offset, mitigates the offset drift, and mitigates the 1 over F noise. Everything is translated to a higher frequency. And one more thing to point out, it has no effect on thermal noise. So the reason is thermal noise is flat, and if you multiply by square wave, you will get the same spectrum in so this math is easily available in any RF books. If you can refer Razavi's, he has explained well that chopping doesn't affect the thermal noise. So this chopper is exactly how a mixer is implemented, but we are using a square wave in mixer. This can also be a sine wave. So what simulation setup we will see today is equally applicable to some simulating some RF circuit, like simulating some mixers. So the same chopper can be used in various other places, which we'll see now is like to generate a square wave current. So if we have a current source and a current sink, and if we use a chopper here, you can see that the output I out. Suppose this is I source and this is the reference 0. We have I sinks at the negative point. When VDD is the high, I source is flowing. When VD is low, I sink is flowing. So positive, negative. So this way, square wave is generated. So this has a very good application in biomedical application for ETI measurement, electrode tissue impedance, bioimpedance. Everywhere, these choppers are used for generating the square waves. And there is also an application which is called dynamic element matching. Uh, when we need to match two current source, the same chopper which we have seen earlier can be used. Suppose we want to match these two current source and the amplitude is a bit different, I1 and I2. You can see the amplitude from 0, I1 is more compared to I2. So what will happen if we have a chopper, and how will I out 1 and I out 2 will look? When the clock is high, I1 will flow, and when clock is low, I2 will flow. If you see effectively the average value, it is I1 plus I2 by 2. So exactly what people do is, especially in current steering DACs, where we have many current sources. So what people do, they use element matching. If there are two elements, we have chopper, and the same thing can be extended to two, three, four elements. So effectively, if we filter out this waveform I out one and I out two, and if we see only the average value, so it is pretty well matched. This is how people are doing precision electronics now in mixed world. So at the heart, everywhere you will find this is chopper. So now to start with the simulation, we'll first see like what is the fundamental difference between simulating this type of circuit and a non-clocked circuit. So it everything boils down to how a simulator works. If we see that, if we see this in the screen and we have a non-linear circuit, we have a diode and resistor and a voltage source. If we want to calculate a VD and ID, how can we calculate? So, like linear equation, like ax plus by is equal to c or cx plus by is equal to f. This type of equation can be solved very easily using matrices, determinants. But this type of nonlinear equation is cannot be solved linearly, and here the simulator really helps. What the simulator do? It solves two equations by Newton reference method, which is in engineering mathematics we all have studied. So it starts with an initial guess and it iterates and just comes to a solution. So this is the approach by which a simulator solves this ID and VD. So there it is important that we need to, in Newton Raphson, we need, if you want accuracy of 4 decimal places, what we do is we stop when after 3 or 4 decimal places, we are getting the same result. Similarly, in simulator also, we need to set that how much accuracy we want. So it is important. Now the second one way is to solve graphically. This is for completeness. It's not related to simulation. Like this type of equation can be solved using graphs also. So how we'll do those analysis in cadence. So whenever we have any bias circuit and a voltage source and a resistor and diode, so we'll have due to the DC we'll have this capital VD and ID, and for AC we'll have VD and ID. So what a simulator does, if you want some AC analysis or if you are doing some noise analysis, first it does a DC analysis on it, and it calculates this VD and ID the same way it is done here. Then it uses this ID in then it linearizes the circuit for small signal, and then it uses this DC to plug it here and just gives you the value of AC, that AC analysis. Or if you see noise analysis, like here I have a slide in which suppose if we have a transistor, same thing we can do. For DC, it will calculate the value of ID, VD, and with this value, it calculates the GM. Similarly, if we are doing noise analysis, what it will do, it will calculate 4 kT gamma GM is the noise of the transistor. So this GM is calculated by first simulating with this, getting this DC value. So now, what is difference between simulating this type of circuit and with chopper? So the moment we put a chopper, we are just changing the schematic with time. So in that way, we cannot have a single DC operation and calculate the noise and AC and every simulation can be done. For that, we need to do PSS analysis, periodic steady state analysis. The idea behind PSS analysis is, in our case, since we are using a square wave, it has only two states. Let me show this. Either it has VDD and 0. So what happens is the circuit is only in two configuration. But what if we have a sine wave in this clock? So there are various DC operating points we need to call, because that's not a small signal analysis. That's why we need to every time calculate the DC operating point with time. So for that we will see the steady state analysis for our work. So is anyone having any question? We can take, we have good enough time. or if something is not clear, we can discuss.
No, Meraj, I think it's clear up to you.
Okay, fine. So what we will do is for simulating differential circuit, uh, there is some while we are simulating cadence, and if it is a differential circuit, we need to have a single voltage source to. Okay, there is a question like what is periodic PSS analysis? PSS is periodic steady state analysis. It is a DC analysis which is done at different instant of time. If we do a static circuit like this, if we don't have any clock in it, so it calculates DC once and then it calculates the noise and AC or whatever parameters you want to, whatever analysis you want to do. In switching circuit, what we are doing, we are changing the topology with time. First input is connected in one way and then with clock it is changing. So there we do PSS for calculating DC operating point at different locations. In our case, we'll have only two different operating points since it's a clock with two levels only. So it's just two DC operating. But if we use a sine wave for, suppose if you want to simulate in a mixer, if you use a sine wave, then you need to see like you need to simulate at a different points on the sine waves, calculate the DC. It's a simple DC analysis with time, and it is also sometimes called like large signal analysis. Means with time when operating point changes, how we'll calculate the noise. So we'll see the setup in our second part of the simulation, the second part of our talk. Now, for simulating a differential circuit and a single-ended circuit. So in CMOS, mostly we use single-ended circuit, means we have only ground and we have only VDD. We will not have minus VSS. So all our input to our amplifier, choppers, everything need to be shifted a bit, uh, anything in between the supply rails and the sine waves can be given like this. So how we can we make this thing in cadence is simply using voltage controlled voltage source. So there is the reason behind using this type of topology. We need a single source for calculating the input record noise. So if you see like if this is VAC and if we have a DC source like this, so what output we will get? The input is the differential input is VAC, and if this node is connected to VDC, we effectively will get VDC plus VAC, and here we have minus 0.5. Here we get VDC minus VAC by 2. Effectively, in time domain, we need a signal like this to simulate our chopper amplifier. So these are some acknowledgements from where we lecture slides, and that's total what I have for our theory part. So now what we can do is, if anyone has some questions, we can take it here, or we can start our demo simulations on this. Topic.
Meraj, chat box, what is PSS? That question is being asked.
Yeah, I PSS is a DC analysis which varies with time. Means whenever we have a switching circuit, we need to calculate multiple times the operating point. That is the PSS analysis. So we cannot simulate it this type of circuit with a traditional approach. So that's why this PSS is there. It is a simple setup which we need to do once, and thereafter you can simulate any switching circuit, even auto zeroing, which I have not covered today. That can also be done. This type of simulation can be done with PSS. This can also be done. Anything else? If someone wants to ask, or we can start our demo session. No answers. So I will start with the demo session then. Fine, Professor Rathod?
Yes, sir. Yes, yes.
Okay.
Acha, somebody has asked a question. Please show one. Just a minute, let me go to chat box. It has gone. Please show one CMOS chopper circuit.
Yeah, that is what if I do in simulation, this is what I will show, like how exactly we can. So the motivation for today's lecture was to practically show and so that anyone can reproduce this type of circuits in the. So I will cover this exactly one by one, how I take the transistor, how I make a chopper circuit. So that will come in our demonstration. Okay, fine, we'll start the demonstration. So first, let me make a library. I will call it like DOC. I have to attach a technology library which we have. You can see this is for the models for the transistors like T values, mu, and CRs, all these things. So first I will make a simple NMOS chopper. So how I can make is I need a transistor. So I will use a so what I'm doing is I need to make this. So this is what I'm making. So now I will add some things. So now I need what I need now is inputs are done. Now I need clock and clock bar. I will use CFK clock, and this is our clock bar. Now, to make it as a chopper, we need to apply a clock bar here. I will label it clock and so this node where it should be connected. It should be connected here, and this node should be connected here. So I will put the label IN and IN. So is it fine? Is it the exact implementation here? What we are saying? So there is a question like how WL of a transistor to be chosen for chopper. The first thing is it should be as low as possible. We try with minimum size so that the the minimum size is chosen so that we don't have any drop, and for speed reasons also. And sometimes we need to increase the width to reduce the around if we have a very high current flowing through it. But for low power application, everyone chooses the small size. And the one big reason of using the minimum size is like we need to reduce the charge injection problem and clock feed through. So that's why if we have a smaller transistor, we can avoid this type of problem. So now it's fine. This input, when clock is high, input is equal to output, INN is equal to output. And when clock bar is high, this part will connect it here, and this is done. So now what I will do, I will just make a symbol. And this one I have to put a symbol on ground since this is the bulk of NOS. Mm, mm, Now we are done with the chapter part. Now we make a simple OTA. So let's make a very simple OTA. And I will just use so we make a differential pair with resistive load. Now we'll add some plain like this is a simple. Make this equal to the chapter. Yes. Now I need a top level to integrate this. This is our input chapter. We need what we are doing is we are exactly replicating something like this. So now we need it's a vomiting animator. We have a supply of 1.8. So I have a different approach of connecting this instrument. It is a bit organized, so in the end, sometimes it helps a lot in debugging and layout also. So now we need what we need more. Let's see the diagram. We need a clock source, and actually, this V clock or this chopper is a symbol. We need actually two clock sources, clock and clock back. So we will use two V pulse is grown 1.8, and let's make a variable period S clock. Rise time 100 people because in 180 a typical rise time is around 80. Let's keep it a bit realistic. Since these clocks can be generated easily using D flip-flops, we'll have one clock and we use a D flip-flop, and the Q and Q bar will act as a clock and clock bar. So this then almost we are done. Now we need a differential excitation source. We can label these nodes as VIT. We see all those time domain and frequency domain, right? So now what we need, now we need a excitation source. We'll try to make this. For that we need to do gain of 0.5. And if we do plus 0.5 now we have the sign for input. We can give any, for now let's start with DC, let's give 0.1. Since this is the reference we are interested in, so I will keep exactly the half of the supply. And this is positive, we can name VINP. So first we see that all connections are proper and not frequency of 100 Hz. First we'll see that whether this excitation signal is proper or not. It's better first to check individual module each and everything, then start simulation. So, a simple transient analysis in good health. So start our transient. Transient is done. We'll see all these notes. If anyone has issue like or how I'm doing the plotting, even if it is not, if it is too related, but anyone can interrupt me. We can discuss maybe on that. So we are interested in, for now, just to see so we can directly out with this node. So you can see there are,
Miraj,
yeah,
keep mic, keep audio. Audio is little low.
sorry.
Your audio is low. Means
Okay,
you're not
okay,
able.
okay.
Yeah.
Fine, fine. So this is our signal, the DC reference. Since we are using a single supply, we need a DC reference, and we have this well proper differential signal. If you take the difference, we will have a good proper signal. So this is our excitation signal is fine. And now let's see whether, let me just start with the one which we started with, the simple DC source. So now if we see the intermediate nodes, first we label this node. We label it with VA plus and VA minus. And we will add some directly first. We'll see the inputs and we'll see how output is built after amplification and finally after demodulation. It is all transient signal. I guess something went wrong with the okay, both the clock bar and clock was same. So when clock is 0, the clock bar should be 1.8. So this is what I will do again, I will put the DC and we'll see like how square will top of in. So this is 900.5 and this is the average value is this is VA plus. It has modulated our 1 millivolt signal to less than 5, minus 0.5. and this is after amplification. This is after amplification, and this if I merge these two, I think the better way to say is to take the differential. Just a minute. So now we are taking differential. Means we'll see this differential. Okay, we'll see the differential input of all nodes. So we are giving one millivolt differential at the input. This is exactly what we are showing here. This somewhere this we have the some gain stage here. I will introduce an offset. Then we have 1 millivolt minus 1 millivolt, and after application at 7.63. So we have a gain of 7.63, and at the output we get 7.63. So what it did, whatever 1 millivolt we gave, we got here. Now I will introduce an offset voltage here. So let's see how for offset we'll add a DC of 0.1. So what now we are doing exactly simulating this setup. Exactly this. This is 7.63 and this is 0.1, and we'll see the spectrum with the output. See the output and input. Let's go all of these signals. This is 1 millivolt, 1 millivolt. If you take the average of these two, it will the DC value will be 7.63. And you can see that over that DC we have a square wave, which is represented like this the output. We have the information is at our DC, and over that DC we have a square wave. So this is what it represents. So whatever input we apply, it got amplified, and the offset also got amplified because of the gain of the. If you would have a gain of 1, you could have seen that it's nothing. So till now, anyone have any doubt? We then go to frequency domain.
Miraj,
Yes.
there's one question in the chat box, and little louder. Na? Your mic, can you please hold it near your mouth? Some voice breaks actually.
Okay. Your voice is also breaking.
Actually, when you was presenting the PPT, it was clear, but now I don't know, little louder. Either you have to speak louder or take the mic near the mouth. Yes, yes.
So the question is, what is the chopping frequency you have chosen, and will it affect the performance of the design? Yes, chopping frequency. The higher the chopping frequency, the better the noise reduction. So you can see in frequency domain, if you increase the chopping frequency, it will the input will be separated from your non-idealities. So the more the chopping frequency, the more. But at the same time, the more the frequency, there are other switch-related issues which comes into picture. So we need to we should only design what is required, if we have a particular noise requirement, based on that we select the chopping frequency. Ideally, if we have a higher, means these all means modulated non-idealities will be shifted to very high frequency, and a simple filter will eliminate everything. And in terms of charge injection, no. Charge injection is a property of a switch, and yes. Charge injection will affect if we increase the chopping frequency. In more cycle, in every cycle there will be a charge injection, right? It will affect. So this is the demo. You all can try it with different value, and if you can see these spikes. Ideally, it should be a square wave at the output. These spikes are due to the rise fall time of our clock is not infinite. Means I have intentionally kept 100 picosecond of rise time of our clock. The reason is in practical chips we cannot make a very sharp rise and fall. So these are the spikes, which is called chopping spikes. The filter also eliminate this thing, and in the end, after filtering, we get a very good pure DC signal. Now we'll see the how this is related to the offset. What if we give a sine wave to our signal? So what we are doing is we have kept a signal of this blue one, and now let's see what if we give some sine wave of let's do frequency of something good. So this is the output what we get. This. So when the clock is high, the sine wave is there. When clock is low, inverse of sine minus. And you can see that the sine wave is there, and on top of it, there is an offset. So this is low frequency, and the square wave at high frequency filtering circuit problem. So this is in time domain. Whenever you simulate chopping circuit, all offsets will come like this. And if we make it again our offset 0, you can see like how it appears. So this is a sine wave. Amplitude will be around 7.63, the gain of our amplitude. So these spikes after filtering is removed. And so this is the beauty of chopping techniques. Like even with a big offset, we are able to get we recover our signal back. Now what we will do, we will simulate the noise where we will require the PSS and PNOISE simulation. So what is needed is whenever we do PSS or PNOISE simulation, we need to disable our input. So we have disabled our input, the input signal, and now what we will do is we will simulate and see the filter noise component. For that we need to go to PSS. So PSS and DC both are same. What does DC does the DC analysis once and PSS does for every time. So how to calculate how much frequency is there? When we click auto calculate, it finds out the clock frequency, and output harmonic is like how much accuracy we need to, with how much accuracy we need to do the DC analysis. So if it is 1K, so if I put 10, so 10 harmonics means 10K. So this the DC analysis will be done at a frequency of 1 over 10K. So this helps in more accurate result. In our case, there is no issue because we have a square wave, so it's just 2 level. But when we do some RF simulation, the more harmonics you put, the more accurate your results will be. And then we need P noise. We can do a simple noise and P noise. Simple noise means it will not take into consideration the effect of chopping. So let's do both and let's see the comparison, like how with chopping, without chopping, we get better performance. So I am simulating from 0.1 Hz to 10K. So I will select my output nodes This is and here there is we need to select our input source. That's why we made this type of setup. This is our input source. Okay, we are done. This is a simple noise. Now we will do P noise. Again, 0.1 to 10K. This is like how much spectrum we want in the output. Similarly, we need to give the this is simulation. So now this reference sideband is very important because when we are simulating chopper circuit, in the end, whatever input we have, the output is at the same frequency. That's why we need to put 0. But if we use, because reference sideband is 0 and 0 plus 1 will be 0 and input will be output. In the end, after two choppers, whatever input we give, it gives back, demodulates to back to the same. But if we are using mixer, we need to change this field. So this is the only difference between simulating a mixer and the chopper circuit. So now all things is set. Now we run the simple simulation. So we will see like what is the noise spectrum when we don't have any chopper. So I will plot input noise and after chopper, after adding chopper simulation, how the noise improves. Let's do this. So so this is the flicker noise component. If you see this 1 by F noise, and if you see this flat part of the thermal and flicker both on the same line, you see that this is not proper. So one thing, whenever you simulate the P noise, we need to do one more setting. It's all about accuracy. Go to P noise, and that is how we are calculating. So sweep type, let us give logarithmic, and we will use around 100 points per decade. Every decade it will calculate the number of 100 points. Now it will take a bit more time, but the spectrum will be pretty accurate. So it's like how what setup you give, it's matter a lot. So now if you see the simulation at 1 kilohertz, this P noise 1 kilohertz, infinite flicker noise is ignored. This point warning was given because 1 by F noise, if you see the F is in the denominator. So at zero frequency, you will get infinite noise. So that's why you cannot plot those things in a simulator. So what it does is that values is not reliable. You can see this 1K. Actually, it's going to infinite. So this point can be ignored, and you can see that the flicker noise at 1K is there, then 3K, 5K, 7K, 9K. So this is exactly what we were talking about here. Now, due to this chopping technique, all our non-idealities are shifted to a higher frequency, and our signal is back to DC. So this is something we are able to isolate our signal and our offset 1 by F noise and drift. Everything modulates to a higher frequency. So, so this is without chopping, we'll have a very huge noise at near to DC because our transistor sizes are very small and flicker noise depends on the size of the transistor. So now we have shifted and now we get very low noise for our DC measurements. So this is the frequency domain analysis. Since we have a lot of time, we can discuss, and if someone have any question, can please ask regarding simulation setup anything.
This the left graph, no? It is white noise plus flicker noise.
Yeah, this is white noise. Okay, okay. One thing what we can do is there is a very good option in Cadence is go to simulation option analog, and I will turn off the thermal noise so that we can only see. Will turn off and will turn off which noise thermal. Then we need to select which module we want to. What I did, I turned off the OTA thermal noise. So when we simulate now, we will get only flicker. That exactly what will appear. So this is very helpful to options here. So this is exactly the noise spectrum. This is only
Means we can separately analyze flicker, separately white.
yeah, you can separately analyze anything with these options. And what I was talking about accuracy setting when I started this part, uh, this here. So whenever it calculates DC operation or DC operating point, it does Newton Raphson. It take a guess and it calculates, and at what point it needs to stop. Suppose if you are working at a very low offset measurement circuit or very low current circuit, then at that time these options you need to set properly. Otherwise, you don't get results. Here.
Achha, this noise is input referred noise.
Yeah, input referred noise.
Achha.
So every time it's better to calculate input referred noise as we are not interested. If we change the gain noise, we change the PSCB output. So these are rel-tol, V-abstol, I-abstol. So this is what the tolerance when it calculates, when it solves those nonlinear equation. Now the accuracy is 1 micro. But if you are working on nanovolt level signal, you should reduce it to nanovolts. This is it depends on the how accurate you want. Otherwise, if we make a chip out of it, we'll see that later that it's not working what we designed for. So simulator settings is really important whether we do whatever analysis. So we should know at least how we need to set based on requirement. And the other drawback is if you set it very low. Suppose if you're working at microvolts level, set the signal level, and you put it nano or pico. The problem is it will take a lot of time because this iteration will go on till we don't get accuracy of 5 digit, 6 digit of decimal places. So these are some important aspects which we need to consider. And one, since we have a time and we are not having any question, so there is one option called result browser for debugging circuit. This is really very helpful, which is in tools and result browser. Whatever analysis we do, uh, it comes here. Like now we have run a P noise, tran, all these things are there. PSS, so we can get all these parameters, individual components. What are the noise of each and every component? What is the flicker noise component of this I0? Flicker noise component of this thermal noise component, flicker noise component. RD and RS is the source and drain noise. This is the total noise. So here, in this result browser, we can debug each and every get to know the information of each and every transistor. So this is a very helpful when we work with some very huge circuits. And if there is also, we can calculate the RMS value of noise while going to result, print, and then noise summary. So since we have done two noise simulation, one is simple noise, which it doesn't take into consideration the clock, and this is the P noise. Now whether when we want integrated noise, we need to see, like suppose we want to design a circuit for application from 0 to zero point 0.1 to 100 hertz. So the higher limit, we know that we will 100 hertz is the bandwidth. So why we select 0.1? 0.1 is the lower limit determines that for what time your circuit is going to work. If you need a 1 second operation, then from 1 hertz is fine. So the lower limit is always determine the observation time. 1 by T observation is this number you need to put. Suppose you need to analyze or calculate the noise of a system which will work for 10 seconds. So this you need to put 0.1. And now let's see, these are the noise component of each. The input referred noise for our bandwidth will be this 2.48 microvolt per RMS of this amplifier. And without, if you see chopping, and if you do the same thing, it's yeah, it's 17 micro. So the noise has reduced around 6 times lower only because of chopping. So if we increase the clock frequency, this noise will further go down. So this is the advantage of very. So in summary, if I want to conclude, chopping technique is used where we need a very low noise, low offset, precision, and circuit design. That's it. So any other question?
This is current mode. This is voltage mode technique, right? That day, madam actually, Shilin madam also explained dual chopping and
Yes, yes.
current mode techniques. She also told about it. This is the
Yeah,
voltage mode.
yeah, this is voltage mode. We are giving voltage. And if we do the modulation in current, that is current mode. So this chopper, actually that work was something similar to this. So here also we get a square wave. If we see, uh, if we have a voltage input, if we use a modulator, we'll get a square wave output. Now, if we have a current excitation in square wave, and if we pass this current through a resistor, so the output will be similar in what we have in voltage mode. So here, what she covered was like for resistance measurement, bioimpedance applications. For there, we need a excitation, current excitation. So the principle is exactly the same. This chopper is removed, and we have a square wave current which flows through the resistor. And yeah, that's it. The idea, the simulation part, everything is similar. We have the same setup for that. So this amplifier can be anything for that purpose. We started with a simple one, and lots of papers nowadays they are using multiple chopper called nested chopping, which Professor Mariam has also discussed. So what we do is even in this voltage mode, we can have nested chopping. We can use four choppers. One will work at smaller rate and other will for a higher rate. That helps in reducing the noise further. So nested chopping technique is also in literature. But whatever we do, the basic idea behind is but since our input and non-idealities are at the same frequency, what we do, we modulate it to a higher frequency and then let the non-ideality come in and then separate out. This is the main idea behind all this chopping technique. So, any questions?
But these transistors, they are like kind of digital circuits. say, past transistor logic, they are connected in series. So
Yes,
this
yes.
channel charges and this clock
Yes,
directly coupled to your other terminals like source and drain.
yes, yes.
Those effects will be considered.
Yes. Clock fit to charge injection are there. These issues are there in all choppers. So that adds to an error. That's why we say that we are able to achieve microvolt level of accuracy. If these issues were not there, we could have got accuracy in nanovolts. There are people who have reported that nested chopping technique. In that, offset can reach to 200 nanovolts easily. So to address that problem, clock injection, charge injection, there is a technique called nested chopping. So if you can read those papers, that will be pretty clear. The simulation setup will be exactly the same. We will copy this module and we'll add one chopper here and the next chopper and we'll have a different clock. So simulation setup will be exactly the same. So I didn't add many things because the reason was like let's learn something from very scratch and later build up from that. Just doing so many. That's why I didn't sim. That's why I made each and every transistor right here. I could have just simulated my previous designs also, so that you can see like how it is made. There is a question in open source LT-SPICE tool. I'm not sure if PSS analysis is there, then only you can simulate this type of thing in open source. Because normal AC and noise analysis won't work with this type of circuits.
Noise analysis is there, but then not in so detail. The cadence is not so much.
Yeah, no. There is a question in chat box like in LT-SPICE tool, can we build this type of circuit? So the answer is if they are providing PSS, then PSS and P noise, then only you can simulate this type of circuit. Oh, this what I'm saying is an answer to the question in a chat box.
Yes, sir. Yes, I am also complimenting that. See,
Okay.
in LT Spice, there is an option
Yes.
of noise simulation, but
Okay.
then, but it only when you select a noise, it doesn't
Yes.
it doesn't give so much detailed simulation. Like,
Okay, fine.
etc. Yeah,
Yes.
it's only basic noise simulation.
I'm not sure like whether maybe they have added. So nowadays it's very common. Maybe they have added.
Okay, they might have. Okay. So which technology you're using for this? What you
We
you- you are
180
using?
nanometers.
180.
What Professor Maria presented was the same 180 nanometers. So it is fine at 180 because our chopping frequency is hardly 10 kilohertz we work on. So
Yes.
this technology is pretty well. Even the same technique you can use to simulate RF circuits, mixers and all.
Yes.
So PSS, PMOS. There is also one PSC analysis which is equivalent to normal AC analysis.
Anybody wants to ask any other question? Very nice. Small but very interesting things he has covered. Anybody would like to ask anything?
Technology nodes used for biomedical applications. Technology nodes, if you ask me, there is why we go for a very lower technology nodes like 65 nanometer. The only reason is for speed. But for biomedical application, if you see what is the highest bandwidth of a signal you want, if you see ECG, it's just 150 hertz. If you see the neural signals, it will hardly go to 10 kilohertz. So we don't need a very fast technology. See, if we use 65 nanometer, you can do it the same thing in 180. Even 350 nanometer can do what we are showing here right now. So application wise for biomedical, you don't need a very good technology, very costly technology. But people are doing it in 65 only because they are integrating SOCs, like they are putting processor on chip. So what they do, they acquire biomedical signal as well as they do every type of processing on chip. There they utilize the for computation, the digital part. For the digital part, they are using very lower nodes. Hope that answers the question.
Yeah, I think there are no more questions.
The technology node affects the technology nodes. Yeah, it will affect because if you go to lower technology nodes, flicker noise is a bit improved. So noise performance wise, we will get some benefit, and the digital part, especially if we see these clock sources, they are can be easily implemented. So you can go to a much higher chopping rates and all. That will give you benefit in terms of speed for digital. If input from sensor is currently very low in which type of photo is preferred? So if you want current sensing, then trans impedance amplifier is a good option which converts current into voltage, and they are using chopping techniques. If you see some latest paper, they will have this to reduce the noise. I think PIA is a very good option. Input bias is also in nano. So there are ways in which people have reduced circuit techniques. They can reduce the bias current. So in chopper amplifiers, it also has a non-ideality of bias currents that has been corrected a lot. So if you are talking about some commercial IC, you can use LMP series IC 900 I don't remember exactly. They have I think in picoamperes of bias current. If you are using commercial IC from TI, so they are using the same bias current cancellation in their design. Yes.
I think questions are over.
Okay.
So, I'll, I'll just remove your presentation, access rights.
Fine. Fine. Fine.
I'll just put it because sometimes it's Sneha madam?
Yes, sir, I'm here.
Yeah. Thank you, Miraj. Thank you very much for accepting the invitation. And it's always difficult to share the live demonstrations, creating this live circuit and then showing is always a difficult part. And with the tools like Cadence, it's really difficult. So thank you very much for accepting the invitation in spite of your busy schedule. You were ready to give some time. I know doing the research at IIT Bombay, they will not give you 1 hour also. Thank you very much and kindly accept this virtual memento, we call it as a, or
Yes.
certificate you can
Yes.
say from our side. So thank you very much. Thanks a lot.
Yeah.
And we'll be in touch with you whenever we have any course or anything related to mixed signal domain or VLSI domain. Thanks a
Yes.
lot.
Yes. Yeah. Yeah. Welcome.
You nicely covered the small concept of chopper, but I liked it. You understood it in 1 hour very nice. At least I understood it very nicely. So that's why I liked it. So thanks a lot. Thank you very much.
Yeah,
So,
if any feedback is there for some improvement, you can also give it to me since I'm presenting for the first time.
no, it's okay. It's nice. It was nice. Simple concept, simple example. Voltage chopper, and you explain it properly with theory, and then supported it with the proper solution. Thanks a lot. Thank you very much. Yeah. So participants, tomorrow we will meet morning 10, and Mohammed Hassan sir, you already experienced him in STTP1, very good speaker, and it was his favorite topic, low power architectures. So please join morning 10, and evening also we have Shaila Subbaraman ma'am. So tomorrow we will definitely have an exciting session. Okay, unless there are any other issues, we pray that there is no issue. So we have definitely exciting session morning also from Dr. Mohammed Hassan and evening from Dr. Shaila Subbaraman ma'am. So thank you very much. We'll meet tomorrow morning, 10 a.m. again. Thanks a lot. I'll close this meeting. Please fill your attendance sheet and feedback form. And tomorrow we will have quiz. कल quiz रहेगा morning. Please appear for that. Kindly appear for that. Thanks, Miraj. I'll close the meet.
Yeah, okay, thanks.
Okay.